Alright, this is section 5.2, Logarithms and Exponential Models, and we have been practicing log equations and solving log equations for the last week and a half, making your eyes bleed so that you can be very proficient at that. So what we're going to do now is actually use these for word problems and to see how you can use it for doubling time and half-life for exponential growth and decay models. So what we do for doubling time, just for a little background, and I'm going to put half-life over here, is scientists use this to look at models to see how certain populations are growing or decaying, and it's a reference point, if you will. So usually when we're talking about half-life or doubling time, okay, we use the continuous model. But I'm going to show you both, but usually it's continuous. So I'm going to say y equals ae to the kt. So there's our continuous model. And remember, when it's doubling, your k is going to be positive. And if you were going to solve this to find out what the doubling time is, you're really looking for the time that this population doubles. So in this y spot, I'm going to put, all right, I'm going to say I want to know when this population is going to double. All right. Now, sometimes you get a number to do that, and sometimes you don't. So we're going to practice problems like that. If I was doing doubling time with our other formula, our annual formula, it's y equals ab to the t. It'd be the same thing. I'm beginning, my initial value is a. I want to know when my population is doubling. So you would solve for t in this case also. For half-life, you're going to have y equals ae to the kt also, but you know that your k is going to be negative because it's decaying. So here's where my initial value, so I want to know when my time, this is half the population that it was. So I have a half a equals ae to the negative kt. So that's how you do half-life, is you want to know when half of it's gone. And with the other formula, your annual formula, you have y equals ab to the t. And here's my initial value a. I want to know when half of it is gone, how long it takes for half to decay. So there we go again. So you have both models. And we'll be talking about that. But I just want you to know, most of the time when you're talking about doubling time and half-life, you're using continuous functions. So please make sure that you're aware of that. Continuous is usually the way to go. Okay, now the logarithm in exponential models here is the log function is often used when answering questions about exponential models because logarithms will undo the exponential functions. We used to solve many exponential functions, and we have been doing that, but now I want to use it in a real-world context. Okay, so here's our first question, and we've done something like this, and I actually forgot the word thousand here. It says, in how many thousands of years will it take for carbon-14 to decay to 25 micrograms? Okay, so here I started out with 200 micrograms, and I want to know how long it takes for it to decay to 25. And this I can tell is decaying because it's between 0 and 1, so everything looks good with my formula. So if I want to find out when I'm solving for the time, this is where the logs come in handy. So I have right here, I have 25, and I'm going to divide it by the 200. So I have 25 over 200 equals 0.886 to the t. And then I know there's no any more normal math to do, so I'm going to natural log both sides. And when I do, I have t natural log of 0.886 equals the natural log of 25 over 200. You can reduce it if you want, but it's not necessary. And then since these are multiplied together here, to unhook them or get rid of that and get the t isolated, I'm going to divide by ln 0.866. And when I do that, I'm out of room here, and you put that in your calculator, it's going to be roughly about 17.18 thousand years. So what I was having you do before in class was actually graph the first model, and remember life is in quadrant 1, so here's time and here's the amount of our in micrograms. That's milligrams and micrograms. And this is time in thousands of years. And here I have 200 and it's decaying. And you found when it's 25, and then I had you graph the left and graph the right, and you found it. But now you can actually use logs to do it, which I think some of you will be very pleased. Example number 2. The U.S. population, P in millions, is currently growing according to the formula below, where T is in years since 1995. When is the population predicted to reach 300 million? Right? So I look at this, where do I put the 300 million? Well, I start at 299 million. I want to put it in this spot, so I end up with 300 million. And I just have to write 300 because it's the equation's in millions. E to the 0.009t. Now I know this is growing continuously, and it's growing continuously 0.9% continuously. So when I get this now, before I used to have you graph it, now you can just solve it mathematically, so we can divide by 299. So when I do, I have 300 divided by 299 equals e to the 0.009t. And I'm going to natural log both sides because there's no other ways to solve for t. And when you do this, I can say on the right, thanks for playing, because natural logging base e undoes it and it turns to 1. So now I have natural log of 300 over 299 equals 0.009t. And to solve for t, these are hooked by multiplication, so I'm going to unhook it by division. So t is natural log of 300 over 299 divided by 0.009, which is roughly 0.371 of a year. So in this case, for it to go to 300 million, even though it's growing 0.9% continuously, it's not even going to take even half a year for that to happen. Okay. Example 3. The population of City A begins with 50,000 people and grows at a constant rate of 3.5%, and it's annual. So as you can see, we're using the A, B to the T formula. And the population of City B begins with a larger population of 250,000 but grows at 1.6% per year. The question is, will City A ever catch up to City B? So even though this is growing faster, this is growing slower, this started out with a lot more people. Well, in order to solve this, is if we set them equal to each other, then we can figure out the time where they're the same, because eventually they're going to cross because their growth rates are different. So we're going to put them equal to each other, and then once you set them equal to each other, you actually kind of don't have to pay attention to the original problem. You can just do the algebra, and this is going to be easier than some of the problems I actually have been having you do for the last week or so. So once it's like this, there's several ways that we can do this. We can go this way and divide them out. So I'm going to actually just divide by 250,000 each side. So when I do divide by 250,000, I have 5 over 25. That reduces down with all those zeros. Equals, and then I'm going to take this and divide it over here. So when I do, I have 1.016 to the t divided by 1.035 to the t. Now recall, if this is both raised to the t, I can rewrite it to say 5 over 25 equals 1.016 divided by 1.035, all of that raised to the t. Now when I get to this point, I can natural log both sides and come up with an answer. So I have the natural log of, really 5 over 25 is 1/5, equals t natural log of 1.016 divided by 1.035. And then I can divide by this because I'm trying to isolate the t, so I can divide by that glop, as I always say in class. So t equals the natural log of 1/5 divided by the natural log of 1.016 divided by 1.035. And when I put that in my calculator, it's roughly 86.865 years. is where population A will equal population B. So in essence, you've answered the question because it caught up. They now equal each other. So that would be the answer. All right, now we're going to talk more about doubling time, and we're going to spend more time on this in class and practice it more, but I want to give you a basis. Eventually, anything growing exponentially will double or increase by 100%. That's what doubling is. Since its percent growth rate is constant, the time it takes for it to grow by 100% is also a constant, and the time period is called doubling time. And I picked a bunny because bunnies increase rapidly. So again, I will write what we started out at the beginning here is y equals ae to the kt. And I want to know when my initial population is doubling, so that's what you're really doing to your formula, and that's what we're going to be using. So I thought the bunny was appropriate. Now I've got a turtle on this one, so it says find the time needed for the turtle, we don't need the word to here, population described by this function here to double its initial size. So let's first look at what this means is I initially, let me find where I was. I'm getting there. There we are. This one is started at 175 turtles, and it's growing 14.5% per year. So I know eventually the turtles are going to double, so we want to know how long that's going to take to happen. So in this spot here, in the population, we're just going to double it. So if I multiply this by 2, that will show me how long it's going to take to double. So I say, all right, we'll put the work down here. 350 equals 175, 1.145 raised to the t. And then when you solve for this, then you'll find how long it takes for the population to double. So when you start to do the normal math with this, the cool part about this is you do this and you start dividing. When I take that 350 and divide by 175, I get 2. And you're saying, oh, that's right, I just doubled that, so I'm going to get a 2. All right, so there's my equation. And then this is a very simple equation to solve, so we're going to natural log both sides. So I have the natural log of 2 equals t natural log of 1.145. And I'm going to divide by that. So the time it takes for this population to double is going to be 5.119 years. Now, they want to know how long will it take to quadruple that? Well, to quadruple that would be doubling this. So actually to quadruple that, or going 4 times, it would take about 10.238 years. Now that I know the doubling time, I can figure this rapidly. How about by a factor of 8? Well, then you double that. So that's going to take, again, going to be 3 times this if you do by a factor of 8. So it's going to be 15.357 years. So this actually comes in handy when you're trying to figure out, okay, how long will it take for this to happen? And if you don't believe me, you can set up the equations. When I do 4 times, it would be this equation and solving it, which we're not going to do because you'll get that answer. And here is if I quadrupled my population, how long would it take? So you could actually go through and do it right from scratch from the equation, or you can take this doubling time, which is a constant, that now you know, according to this equation, when it's going to happen. You can answer a lot of questions about that. All right, example 5. Now we're going to practice some doubling time, and some of these are trickier questions because you have to make sure that you plug what you need, and you're not always going to get the initial population. So a population doubles in size every 20 years. What is its continuous growth rate? So they want the rate, the k value, if you will. So I have y equals ae to the kt because they said continuous and they're talking about doubling. All right. So it doubles in size. So as soon as I say doubles, I said, okay, I start out with A. I want to know when it goes to 2A. And I'm solving for K, and then it says it takes 20 years, so I can put a 20 in for T. So you don't necessarily need to know what you started out with. Now, if I start doing some normal math here to solve for K, when I divide by A on both sides, it disappears. So I can say, thanks for playing. So I end up with this equation, 2 equals e to the 20k. All I did was put the 20 in front of the k. It looks funny that way. And then I'm going to now, I want to solve for k, and since k is an exponent, I'm going to natural log both sides. And thanks for playing, base e. Gotta love base e. So you got natural log of 2 equals 20k, and I'm solving for k, so I'm going to divide by 20, so k is going to equal the natural log of 2 over 20, or 0.03466. Now, first of all, I'm very happy that this is positive because it's doubling, so that is good. And now we want to actually say, I don't want you to leave it as a decimal point, I want you to tell me what it's really growing. And it's continuously growing, has continuous growth, and make sure you move your decimal place over to 3.466%. Okay? So that's one way you can use doubling time. Half-life. Just as exponentially growing quantity doubles in a fixed amount of time, an exponentially decaying quantity decreased by a factor of 2 in a fixed amount of time. This time period is called half-life. And a lot of times, I'm teaching this around the Super Bowl, so I keep saying half-time, but it's called half-life. So with our formula, it's usually continuous. It's AE to the KT. Now I know the K is going to be negative because it's going to be decaying, and I want to know when half of it's gone, so this is what you end up doing, is a half of whatever your initial value is. Now I don't usually put a negative sign by K. I let it happen, but I just want to demonstrate to you this only works this way. You can't have a doubling time with your K negative. It just won't work. Okay, example number 6. Carbon-14 decays radioactively at a constant annual rate of 0.0121%. Show that the half-life of carbon-14 is about 5,728 years. Well, they did the hard work for us because they took this percent, they moved it over, actually, excuse me, the wrong way. You move it over 2 more places because it's a percent, so you have to divide by 100, and then they subtracted that from 1 to get our B, because 1 minus our rate is going to be what our B is. And they did the hard part for us already. That I didn't have to do that. So they showed this part. And a lot of times you will see Q sub 0 or the beginning quantity, especially if it decays, you'll see a Q. And this sub 0 just means your initial. If this bugs you, use A like we've been using. But I'm going to use what they have in this formula because now I want to know how to show that the half-life is 5,728 years. So if I want half of Q sub 0, I'm going to write that over here. I want to know how long it takes for half of that to go away. And then when I divide by Q sub 0, it goes away, so I have a half equals 0.999879 to the T. And I'm solving for time, and I'm hoping it's 5,728, so I'm going to natural log both sides. So I have the natural log of a half equals T natural log of 0.999879, and I'm going to divide by that, so I have T equals the natural log of a half divided by the natural log of 0.999879. Boy, a lot of nines in there. And that's going to equal roughly 5,728. So I've shown that that is the half-life. So that's cool. It's long, but it's cool. All right. Let's look at example 7. The quantity Q of a substance decays according to this formula, where T is in minutes. Okay, that's interesting. The half-life of the substance is 11 minutes. So they're telling you the half-life of it. What is the value of K? Now, the one thing they did here is the K is already negative. So when you solve this, I'm so saying, yes, it's negative, it's decaying, but they already placed the negative in the equation. So you're going to end up with a positive answer, okay, but K really is negative. So they told you it's a half-life, so I'm going to say, all right, I'm going to do half of my initial value, which is Q sub 0, is Q sub 0 e to the negative, and then I'm going to put an 11 in this spot, so it's going to be a negative 11K. These will cancel out, so I end up with this simple equation. Now all I'm going to do here is natural log both sides. This should be getting used to this part now. So I have negative 11K is going to equal natural log of 1/2. And so K is going to equal the natural log of a half divided by negative 11. And when you get that, you get a positive 0.06301 because the negative has already been placed. So the rate it decreases per minute, it's 6.3, you move it over, it decreases per minute continuously. So that is the value of k. All right, doubling time. We're going to practice some more because this is the one I want to make sure that you have this down pat. A population doubles every 27 years, assuming exponential growth. Find the annual growth rate. Now, they said annual here, so I am going to use y equals ab to the t. And I have to look at the information they gave us. So they said it doubles every 27 years. So I know the 27 is going to go here. So I know I'm going to take a, and I want to know when it doubles. Excuse me, I'm going to say it doubles every 27 years. And so they want us to find actually your b, or your growth rate. So I plugged in that information. The a's are going to cancel. Thanks for playing. So I have 2 equals b to the 27th. Now here's where everybody's so used to logging, like, oh, we have to log that. I said no, because the b is down low. So this is where you're going to raise it up to the 1 over 27. Don't think you're going to log everything. The only time you log it is if it's an exponent. Now when I raise it up, I get my b to come out to be 1.0260, and I'm happy because it's over 1. Move it over 2 decimal places, so it's 2.60% per year is my actual growth rate if a population doubles every 27 years. Okay? The continuous growth rate, now we want to find that one. So now I'm going to use y equals a e to the kt. And I'm going to go ahead and double it like we did before. And they said it took 27 years, so I'm going to put the 27 in the t, and I'm just switching their spots, so it's 27k. Then I'm going to divide by the a, so I say thanks for playing. So I have 2 equals e to the 27k. Now here, the k I'm looking for is an exponent, so now I'm going to natural log to solve for this. Thanks for playing. So I have the natural log of 2 equals 27k. So k is going to equal the natural log of 2 over 27, which is 0.0257. So if something continuously is doubling, the growth rate would be 2.57% per year. And they're a little bit different, and we've talked about many times why this happens in class is because this is continuously growing. The rate can be a little bit lower and still achieve the same results. Now this problem is probably one of my favorites because it really makes you think, and I want to show you how to set up this so you can solve these type of questions. So I have a 27% of a radioactive substance decays continuously in 8 hours. Then they want to know what the half-life is. If you see the comma there, or they want to know the half-life, you got to look at this and say, well, I want to know what the equation is before I find the half-life. So how I want you to do this is we're going to set it up like a T-chart, if you will. And we're going to do the formula first. And then the next thing we're going to do is find the actual half-life. Okay, so let's find the formula. So I know it's y equals a e to the kt. And I want to know and fill in what I have here so I can come up with a type of formula to use. So it says 27% of it decays in 8 hours. Well, I know the 8 is going to go in the t spot, but and I know the e's okay, but I'm a little confused about the rest. So I like drawing some pictures. So here I have this substance, 100% of it. And I like to draw pictures so I can try to understand this. They said 27% of it decays. Well, if 27% of it decays or goes away, what's left over? So if I did 100 minus 27%, I'd have 73% left. So here's A. This is 100%. I want to know, it's going to take 8 hours for 27% to go away, so I'm saying, oh, that's 73% of it. So we change it to a decimal. I say, okay, 73% of A, this is what I started out with, this is what's left. E, I don't know what K is, but I knew it took 8 hours. All right, let me say that again. So here's my initial. it decayed 27%, so 73% of the initial. I don't know how much it is, so that's why you say the A. Now the A's are going to cancel out on you here, but it's pretty cool. So now I have 0.73 equals e to the 8k. And then now k is an exponent, so I'm going to natural log both sides to solve for that. So I have the natural log of 0.73 equals 8k. K is going to equal the natural log of 0.73 divided by 8, or roughly, and I always go for decimal places, 0.0393. So this is a 3.93% continuous decay. Now what this just did was help me, so now I know my formula. Even though I don't know what I started out with, I do know it's AE to the negative 0.0393t. So now at least I can use this to figure out the half-life. But you needed to know the actual, your K, your decay factor, or else you wouldn't be able to find your half-life. Now I used what I found out before, is if I start out with A, I want to know when half of it is gone. So I'm going to do my half-life. And we've done this a couple times. The A's are going to cancel out. Thank you for playing. And so now I have a half equals e to the negative 0.0393t. Natural log both sides. Thanks for playing. So I have the natural log of a half equals negative 0.0393t. Divide by that, so I have t equals a natural log of a half divided by negative 0.0393, which is roughly 17.64 hours. Which in a way kind of makes sense, because if 27% of it was gone in 8 hours, it's going to take longer, so at least that much. And you're saying, well, it's a little bit, 27%, 50% of it gone. Yeah, that kind of makes sense that it's about 17.64 hours. So I wanted to model how you find the formula first and then you do the half-life. Now let's do some conversions here. We're going to convert between AB to the T and AE to the KT. We did this the other way, but now we can do it this way. So I have this population. These were the turtles we talked about before. I had 175, and I'm growing 14.5%. They want us to convert it to a continuous formula. So remember, if I have y equals AB to the T and y equals AE to the KT, the A's match, the T's match, your B has to equal e to the K. So basically, you don't have to rewrite the whole formula, but I can just say, oh, my B right here has to equal e to the K. So I'm going to say e to the K has to equal 1.145. When you do that, then you can figure out what the continuous growth rate, you can kind of go back and forth. Because the K is an exponent, I have to natural log both sides, and I love base E. Thanks for playing. So K is the natural log of 1.145, or, and I go about 4 decimal places here, K comes out to be 0.1354. So my exponential formula is going to be P equals 175 e to the 0.1354 t. Now this one's growing 4.5% annually. This one is a 13.54% continuous growth. So you can convert back and forth fairly easily to do that. So that's what your formula ends up being, and you converted that formula. Let's try it again. Let's convert this one to B. So now I have a continuous formula, and the 7's in the A spot, so remember again, so you have y equals AB to the T, y equals AE to the KT, so B is going to be the same as e to the K. So here's e to the K right here, just this part. His has to equal B. So now I say, well, B has to equal e to the 0.3. Well, there's really nothing you have to do, because you've actually, that is a number. Just put it in your calculator and then you'll get the decimal form, which is 1.3499, or 34.99% annual growth. So my new formula is Q equals 7 1.3499 to the t. See? So that's pretty simple to go back and forth. All right. Let's do one more converting. They want me to find the continuous growth rate. So I have an a, b to the t. This is my b. And I know e to the k has to equal that. So I'm going to say e to the k equals 0.886. And because I know k is an exponent, I'm going to natural log both sides. Thanks for playing. So k equals the natural log of 0.886. So k in my calculator comes up to be negative 0.1210, which I was glad it was negative because it's decaying. And this is 12.10% continuous decay. Continuous decay. So my formula comes out to be Q equals 200 e to the negative 0.1210t. So you convert it back and forth. All right. Now, the one thing I want to show you this, and this is the last slide for this taping, is some equations with the variables in the exponent cannot be solved using logarithms. And I'm going to give you this example, and it's kind of a cool example, but it says within t years the population of a country in millions is given with a food supply of people that can be fed, and determine the year in which the country first experiences food shortages. So here's our population. And this is 2 million people, and it's growing 2% per year. And then here's our food equation, and I can feed 4 million people at first, and I can increase and feed another 500,000 people per year. All right. We want to know when this country is going to first experience food shortages, because it's growing exponentially, and this is basically a linear type of thing. So if you were to look at this, so I actually want to draw a little picture here, is the population here is starting in millions. So here's your population that is growing of millions of people. And this is time in years. Life is in quadrant 1, so we draw this. So basically, this is what the population is growing, because it's growing 2% per year. This is my food equation, so I can feed 4 million people here, and then it's got a positive slope. It can increase 500,000 people per year, but after a while, you're going to notice right here, the food, right now I have more food than I need, but the population is outgrowing it. So right here is where they're going to start experiencing shortages. Well, how do you find that? Well, you thought, well, let's put these two equal to each other. Well, you can't solve it because this is a linear function, this is exponential, and mathematically it's difficult to do. So what you can do is graph it like I showed you before to find out when they cross. And you'd have to have a pretty wide window, so I'm going to tell you the answers, but it's like it would take about 199.38 years, but eventually they're going to run out of food if they don't figure out how to increase this or have the population not grow as quickly. Okay, well that's this part of the exponentials. We have one more section and then we're done.